as I mentioned in the last lecture, we would like to review what we learned in the last lecture. Okay, I don't know whether this review really make you understand the diffraction and scattering and radiation problem at the same time. But let us try at least. The message or objective we had in this chapter, as the name implies, we would like to understand radiation, scattering, and diffraction. Phenomena at the same time. The reason why we attempted to understand that these three looked very different acoustic behavior, along with the sort of unified concept, is because, for example, radiation is, as the name implies, the sound radiating from the body because of its vibration. That is what we normally call radiation. Okay? And the scattering is what we normally say when you have an instant wave and it meets some object in space, and then it is scattered, and then it radiates. So in this case, we said that the total sound field has two components. One is instant sound, and the other one is a scattered sound. And we found that in the last lecture, PT has to satisfy rigid wall boundary condition. In other words, dp dot n, this is the normal direction vector, surface normal, has to be 0. In other words, the velocity of the surface has to be 0. And this has to be pt. So if we use this, and if you know pi, then we can certainly calculate, estimate PSC. That's the basic concept. And then in the last lecture, for simplicity, as a special case of this scattering, we considered the scattering due to the presence of sphere in space whose radius is a. And the scattered field does depend not only A, but also angle theta. Strictly speaking, the scattering field does depend on Ka that measures the size of a scatterer with respect to wavelength lambda. Okay? For the radiation case, we learned the breathing sphere case that has radius of A, in this case 2, as well as trembling sphere case, or we consider the case when it trembles this way. And we found that radiation for the trembling as well as a breathing case does depends on Ka, as well as depends on the observation distance from the center of the either breathing or trembling sphere. In other words, if we are in a far field, in other words, if Kr is very large, that means we are observing sound in the far field with respect to wavelengths of interest. And also the radiation does depends on the scale of Ka also. That scales radiator size with respect to wavelengths. And you remember that the real part of this radiation is proportional to Kr, Ka square 1 plus Ka square, and the imaginary part is simply Ka 1 plus Ka square, things like that. Okay? All right. And then we move to the case in which we have slit. We start with a two-dimensional slit. In other words, we have an infinite, length scale in this direction. And we found that if we regard the size of a slit, okay, in this case, A, this is, I think that is A, okay. Then the sound radiation from this slit does also depends on Ka and Kr, as well as the angle. Okay. And all this case we can solve using famous Kirchhoff-Helmholtz integral equation. Okay. For example, we can write G dp dn minus dg dn P on the surface that is radiating. So if you select G as the monopole and make somehow dg dn disappear, then we can use the simpler form that allow to predict sound pressure at any point, and that integral we call Rayleigh integral. Rayleigh integral first kind or second kind is nothing but when we have this one is 0 or this one is 0. Okay. That means if you do know the velocity on the surface of a radiator, you can always predict the sound. Okay, you have a powerful computer, and you can do it. Any shape of the radiation or scattering, you can calculate. Okay, but what I want to emphasize using this lecture is, even if you got the result, I mean, you have to be able to understand the physics that results try to give you. Okay. To understand the physics, it is necessary to understand the radiation or scattering diffraction of the simpler case. So we expanded this case to the case for which we have this kind of slit and this kind of opening. Okay. The reason why we can say all these cases can be considered along with the unified concept is because this is nothing but the case the wave that is changed due to the presence of impedance discontinuity in space. Okay, this is the case when we have, when radiator is looking at the space with respect to radiation impedance, and this is the case when you have an impedance mismatch along this surface, and this is the case when we have spatial impedance mismatch over here. The impedance of the wall in this case is infinity. Impedance over here is a pressure release impedance, and this is the case when impedance is infinity because this is a rigid wall. When we have this kind of impedance mismatch, we can also use this Kirchhoff-Helmholtz integral equation that describes how the wave is propagating in space. And then we argue that because we do know the sound radiation from this kind of slit or this kind of opening, as well as this, we can also get a sort of analytic result for the case when we only have this. Okay, that's the case when A is very, very long. Then we can get a solution by looking at the half space of this case. That provides us the diffraction problem, so the analytic solution of diffraction problem. And also we can invite another boundary condition over here and boundary condition over there and split it out. Half space solution will give us the analytic solution of the diffraction problem. I mean, you guys have a very strong computer. You don't have to, you can calculate the sound field due to this kind of impedance distribution in space by using this. Either you can use a Rayleigh integral of first kind or second kind, you can get it. But as I mentioned before, it does not provide you any physical insight at all. I do know you have such powerful calculation ability, but I'm trying to provide you some sound, powerful understanding basis of acoustics. Okay, those sound understanding depends on Ka, Kr, sometimes the J1 sine something divided by something. Sometimes it depends on sinc function, blah, 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 as you saw before. And I will repeat in some way to show you how these things are expressed in analytic form today. And this part, as I mentioned to you before, is the most difficult part.